No, I'm good.
I might die over there, so I probably not.
How far down the road is that?
My school?
No. Far down the road.
Okay, so I would like to finish up the 2-1 notes today. So, chapter 2 is shorter than chapter 1. So there's only 2 sections. So once we finish this, we only have 1 more section to do. But I will say section 2, I think I have it on the calendar for 3 days. There's a lot in section 2. So what section 1 is talking about is measures of location in a data set. And we talked about percentiles, and we talked about z-scores. But what we're also going to do is talk about how to transform a data set and how that might impact your placement in the data set. So I asked you to enter in this data. And what I also said here is I backed up and said the formula for calculating a z-score requires subtraction of the mean and then division by the standard deviation. And so the whole concept is trying to get you to understand how operations that you do on a data set, like the subtraction or the division, it will impact the overall data set. And we're going to see how it specifically affects your numerical statistics. All right, so here's a dot plot of these scores from an Algebra 2 test. And I asked you to enter the data in the calculator. And did you get your 1 variable statistics out of there and fill in the first row of the table? Did you do that? Yeah. Can you do that if you didn't already? I don't need passes. Those go in the trash can. All right, does everybody know how to enter data and get the 1 variable statistics out? You're all comfortable on your calculators with that, okay? All right, so I'm on my 84 to begin with. So stat, calculate 1 variable statistics. I'm in L1, and I will calculate, and I'll just go to a couple decimal places. So I'll call X bar 47.11. Standard deviation, remember there are 2 standard deviations. There's the S and the lowercase sigma. For right now, we're focusing on the S. It will always be the larger of the 2. And so for standard deviation, 9.16. And then we can scroll down and we can see some of our other things we have. The minimum is 27, Q1 is 40, median is 48, third quartile is 54, the maximum was 62. The calculator will not give you the interquartile range, but that is just the difference between the 2 quartiles, so that would be 14. And the range is just the difference between the maximum and the minimum, which is 35. All right, everyone's good with that? We all know how to do it? Inspires, 84s, everyone's good. As I look around, I do see a couple of 84s that are a little bit older than mine. At any point, you need to know if your menus, your screens look different from mine and you can't figure out what to type in, make sure you ask, okay? The 84s, there are lots of levels of operating systems out there. And so what you see might not match mine. All right, so in part B, it says, suppose the Algebra 2 teacher was nice and added 5 points onto each person's score. Would I ever be that nice? Okay, so I'm going to go back to my 84 because that's what I had up first. So we don't want to re-enter all the data. Do you remember how to use your formulas that I showed you the one day? All right, go back to your stat, edit. And you can either put this in a new 84s, you can either put this in a new column, or you could rewrite over the original column. I recommend using a new column because if you mess something up, you don't want to mess up your original data set. So what I'm going to do is I'm going to go to the top of the next column, very tippy top, where it says L2. This is your formula line. Okay, this is for 84s. So what you want to tell it to do is you want to tell it to take everything in L1 and you want it to add 5. Okay, so press second 1, And now it says L2 equals L1, and then type in plus 5. And it will now add 5 onto every value for you. So go back and recalculate your one variable statistics off of that now. Inspires, do you remember how to do that? How to use your formula? Inspires, just so you know, you cannot overwrite your old column. You have no choice but to go to the next column. So I'm just going to call this one plus, because that's what I'm doing, is I'm adding something, or add, I don't care, whatever you want to call it. Okay, name your column. And this is your formula bar now. So what you want to do is, I do not know why this won't stay in focus, but it won't, so it is what it is. You want to press the equal sign to let the calculator know that a formula is coming, and then you press your variable button. Now, if you already used your calculator on one variable statistics, you will see a really long list when you press your variable button. Do you see a really long list, Inspires? That's because when you did your one variable statistics, it took all of those things it calculated for you and put them all into the calculator memory for you, okay? So find the one that was your original name. Mine was ALG for algebra. And then I say plus 5. And now it added, now the other thing to keep in mind, Inspires, when you do those one variable statistics, it starts filling in your next columns. So like right now, if I did my one variable statistics, and I'm going to do this now, oh, I want one column, that's all I want right now, and I want my plus column. It will now fill up columns C and D. So you probably already had columns B and C filled up. So then you would use column D, and now it probably has E and F filled up. All right, so let's see what we have here. One variable statistics. Do we have 52.11? Do we still have 9.16? And then I hope we have 32 and 45 and 53 and 59 and 67. And then I would still have 14 for my interquartile range, and I would still have 35 for my range. Do we all have that? Okay, before we go any further, do you notice anything between those two rows? Do you notice anything between those two rows? Julie, what do you see? All right, so the interquartile range, IQR and the range are the same. And what else did you say? Okay, they are different, yep. This stuff is all different. What about standard deviation, same or different? All right, so there are 3 things that are the same. What do these 3 things have in common? What types of measures are the standard deviation, the IQR, and the range? They are measures of spread. Okay, if you go back to chapter 1, we talked about measures of center and measures of spread. And there were 4 measures of spread that I said you need to be familiar with. Standard deviation, variance, interquartile range, and range. Now, we don't have the variance on this list. That's something different, but down here are measures of spread. When we added 5, there was no change. All right, measures of center. Measures of center are things like the mean, the median, the mode, and the mid-range. Julia's right. The measures of center are different. Can we be more specific? They got bigger by 5. Because what did we do with our data set? We made the data set get bigger by 5. So if you added 5 to every value of the data set, your measures of center will also have 5 added. Your measures of location, like your quartiles, will also have 5 added. And I put down here, this is just something I put on the end of this table just to remind you of something else, make kind of related to something you would have done in my class a couple years ago, either last year or 2 years ago. Do you remember doing my little chart method of graphing? And I had this thing called an HTR5. Do you remember what that was? A horizontal translation to the right by 5. Okay, so this is a graph. Now, I don't have an x-axis here, but I could. There could be an x-axis here and a y-axis, and the y-axis would be my frequency, which went anywhere up to 3. A horizontal translation to the right by 5 means that this data set just gets moved to the right. And if you think of it that way, doesn't it make sense that everything gets pushed up by 5, the minimum, the maximum, the median, the quartiles? But if you just shift the whole data set by 5, the spread doesn't change. It doesn't make it get wider, or what did we call those things in algebra? Things that made them get wider or squishier. Stretches and compressions. This is just a translation. You moved the data. So a measure of spread isn't going to change, but the measures of location will change. And they're going to change in the same way that you made this change. So adding 5, or if you were subtracting 5, okay, that's just a horizontal translation to the right by 5. It's not going to change a measure of spread. All right, so now what we're going to do, we're going to say, suppose the algebra teacher was really nice and added 5% onto a person's score. Okay, 5% means 0.05, but if you multiply everything by 1.05, the multiplying by 1 means take the original score, but then the 0.05 says, but make it bigger. So what you're going to do is you're going to take everything in your first column, whatever you called it. I called mine ALG for algebra. So I'm in my Inspire, I'm going to go to the next open column, and I'm going to call this one MUL for multiply, because that's what I'm going to do in this one. I'm going to multiply. All right, in my formula bar, I'm going to say equals variable. Okay, here, now I finally have a long list because I did one variable statistics. Your list is even longer if you've done one variable statistics twice. Okay, you have 2 sets of all that stuff. But the bottom line is I want to use that very top one, ALG, and I want to multiply by 1.05. All right, so it just did that for me. So now I know what everyone's new score would be if I was ever that nice of a teacher. All right, so I want you to do your one variable statistics on that. And 84s, just to refresh you, again, go to the top of the next column. That's your formula bar. You have the equal sign built in. So you just go back and say, take everything that's in L1 and multiply by 1.05. There's our new set of data. Stat, calculate, one variable statistics. I want to switch now to L3 because that's where I'm at. All right. And so these are the numbers that I have. I have 49.47 approximately. I have 9.62, 28.35, 42, 50.4. Are these matching yours? So I want to make sure I have everything corrected, my calculator. All right. So do you notice that everything changed this time when you compare it back to the first row? What do you think everything changed by? How do you think this 47.11 is related to that 49.47? How do you think that 9.16 is related to that 9.62 and so on? What do you think happened? You're lucky she's here because she's getting them all right. Yeah. Everything got multiplied by that 1.05. The measures of center, the measures of spread, the measures of location. Because when you multiply by a 1.05 back in algebra, that would have been a horizontal stretch by a factor of 1.05. So everything got expanded by that amount. Okay, so not only did each number get bigger, it got bigger to the point that it changed the spread. So instead of being here to here, okay, the smallest number actually got pushed up a little bit, and the largest number got pushed up a little bit more, and it increased the spread, and everything gets impacted by that same amount. And the same thing would happen if you divided by something. Okay, so if you go back, how this is related to what we were talking about last week, it goes back to this formula, that if you take a data value and you subtract the mean, every data value is getting subtracted by the same amount, so they're all getting shifted down the number line the same way. And then when they get divided by the standard deviation, that's now all getting horizontally compressed by the same amount. So you're keeping everything proportionally the same, okay? So this formula is just allowing us to convert everything to a proportional scale, but what we call a standardized scale, where when you turn things into z-scores, everything is going to be centered around the number 0. Because if you have someone who is exactly on the mean and you subtract the mean, that's going to give you the 0. This formula puts everything on a scale that is centered at 0 and then goes out by 1 standard deviation. Okay, so if you go back to the exercise that we did in class with our heights, the standardized scale, when you convert things into z-scores, you convert everything into a center of 0, and then you add 1, you add 2, you add 3, and you subtract, okay? We call them standardized scores because it puts everything on this standardized scale, okay? Now we're going to talk more about z-scores and the bell-shaped curve in section 2. The rest of section 1 just talks about something called a density curve in general. And this actually comes up a couple different places. So a density curve is, you have to imagine that when you collect data and you draw, whether you make a dot plot or you make a histogram, we make these bars that are very geometric. And by the way, juniors, when you take AP Calculus next year, you're going to do something very similar to this. So you could find the exact area of the rectangles because you know the formula for finding an area of a rectangle. But as you've seen me do already, and I've been watching you do this a couple times in class, you're already learning that even though you might have a histogram, you kind of look at it and say, but does it kind of follow a curve? Okay, that curve is called the density curve. So even though your data might look like a jagged set of a histogram, it actually comes from, if you had enough data, it would fill in that curve perfectly. And again, juniors, next year in AP Calculus, you are going to start by finding area of these rectangles to estimate the area under a curve. But next year, you're going to learn how to find the actual area underneath curved graphs. Very cool, okay? So the density curve is the curve that we draw that kind of follows the path of the histogram underneath. The density curve should give a clear picture of what a complete data set would look like, what we call a population. Typically what we do in statistics, though, we don't have the population data. We just take a subset of the population called a sample, and we graph that. And that's why it might not line up exactly, okay? So the population is the whole group. Like if we did heights of every high school student in the United States. Okay, that could be our population. You are one tiny subset, which is why your histogram would not fill up the density curve. Okay, there are several basic criteria of any density curve. The curve will always be on or above the horizontal axis of a graph. Okay, technically, by the way, the horizontal axis is an asymptote, and technically those tails never touch the x-axis, though in real life it sure will seem like it does. The area under the curve must equal 100% of your data, okay? Because the density curve, again, is supposed to represent a population. Well, if you have 100%, if we move the decimal over, that equals 1.00. So that's why we say the area under the curve is always equal to 1. Any portion underneath that density curve is going to be a portion of 100% or a portion of 1.00. We use X bar and S, which is the same as SX, by the way, to represent the mean and standard deviation of actual observations, a sample. Okay, so back to our height exercise. We calculated the mean of our sample and the standard deviation of our sample. Would that actually equal the mean and the standard deviation if we knew the heights of every high school student in the US? Probably wouldn't be exactly the same. If you actually know the mean and standard deviation of the entire population, now we switch to the Greek alphabet. And we would say the mean is now called mu, and the standard deviation is now called sigma. And these are lowercase Greek letters, okay? So when we use these, X bar and SX, those are sample statistics. When we switch to mu and sigma, we call those population parameters, okay? So again, section 2 is going to focus on this bell-shaped curve. What I'm going to do in this last example is show you an easier one, because distributions come in many shapes. If you go back and look at chapter 1, one of the notes I showed you like 6 different pictures. We had the skewed right, the skewed left, we had the bell shape, we had random, we had uniform. I was showing you all the different things that you might see in a distribution. I'm going to start our calculations with a uniform distribution, because a uniform distribution is flat, okay? And therefore, if it's flat and the area is always equal to 1, we actually can base our calculations on an actual perfect rectangle, okay? So the amount of time that a person must wait for a bus is uniformly distributed between 0 and 15 minutes. All right, so if I were to sketch a graph of this, I could say that the x-axis is measuring time in minutes. And what I'm going to do is I'm going to label my y-axis. I'm going to label these as relative frequencies, percents, so that I can think about my uniform distribution in terms of percent or parts of the whole. So if I know that it's a uniform distribution and it goes between 0 and 15 minutes. So here's 0, here's 15. A uniform distribution means it's completely flat. So it is a flat line. So the graph would literally look like this. It's just going to look like a flat line. And what you do at the end of the flat line, and it stops at 15 minutes because they told me that people only have to wait anywhere from 0 to 15 minutes, you drop a perpendicular at the end of your uniform distribution, and you drop it at the end of your x-axis. And it makes a perfect rectangle. Now, you know the formula for area of a rectangle is base times height. How long is my base? 15. And the area, because this is a distribution, a uniform distribution, how big is this area? It's got to be 100%, but I'm going to call it 1 to represent the 1.0, which is the same as 100%. So how tall is the rectangle? What's the height of my rectangle? Not a trick question. 1/15. And I would expect you to be able to think that through on a test. Okay, it's not super challenging. You just need to understand that underneath any distribution, whether it's uniform, whether it's bell-shaped, whether it's bimodal, whether it's right skewed, left skewed, all the area underneath is equal to 1 or 100%. Okay? So now, what is the probability that a person waits fewer than 6.5 minutes? Well, if we went fewer than 6.5 minutes, 6.5 minutes would go, there would be a mark along this axis, let's say probably right about here. Draw a perpendicular at 6.5 minutes. If you want to answer the question, what is the probability that the time a person waits is equal to 6.5 minutes, or excuse me, is less than 6.5 minutes? All you need to do is calculate the area of that region. Well, that region is its own rectangle. That rectangle is 6.5 minutes long along the base. I know the height is 1/15 because I just calculated that. So the answer is 6.5 over 15, which is the same as 65 over 150, which you could divide out. I have it's 0.43, which would be the same as 43%. So if this really is the distribution to represent how long people wait for this particular bus, you could now say that the probability that I wait less than 6.5 minutes, there's a 43% chance I will not have to wait more than 6.5 minutes. Okay. Now, could you figure this answer out without using the 6.5 times the 1/15? You sure could have. You could have said, well, 6.5 is, you could say 6.5 out of 15. Some people would have jumped right to this and said, yeah, proportionally, it's got to be this one portion out of the 15-minute block. But this is technically where it's coming from. So now it says, what is the 90th percentile of wait times? All right, well, the 90th percentile, if that's a percent, it means what I'm talking about is 90th percentile. I'm going to mark it like maybe right about here. To be the 90th percentile means that must be higher than 90% of everything else. So what that tells me now is when I draw my perpendicular, I actually am dealing with this whole area right here, that whole region, the whole thing now. Oh, it looks almost like an American flag. So 90th percentile though, I'm going to put that as my portion out of the 1. So I'm going to put the 0.90 on the side for the area because I want 90% of the area. I don't know how many minutes that is. That's going to be my unknown base. And I know my height is 1/15. So the B value would have to be 0.90 multiplied by 15, which is 13.5 minutes. So in terms of what that means waiting for the bus, 90% of the time you will wait less than 13.5 minutes. 10% of the time you're going to be waiting a little bit longer. And that is section 1. Not too bad, is it? Okay, so quick recap. Not that it's not all important, but make sure you know how to calculate percentiles. Make sure you know how to complete a frequency table with the cumulative columns. You know how to make a cumulative graph. And one of the things I'm going to point out is go back and remind yourself about how I said the first dot always has to be at 0. And remember, the x-axis is just a normal scale. Do not mark an interval like 35 to 40, and then 40 to 45, 45 to 50. It needs to be scaled like a normal x-axis. You should know how that shape is related to the shape of the original distribution. You must know this formula. This formula is kind of sort of on the formula page, but it's not super obvious. It's easier, just memorize that formula. You need to know how to calculate a z-score, and then the stuff we did today. All right, we good on section 1? You can finish that homework?